Hello students. So in the last class we looked at some of the simple processes and solved example problems for material balances on operations which were single units without reactions. In today's class also we will continue the same. We will look at some other processes and perform more example problems to get ourselves familiarized with the systematic approach of material balances. Leaching and extraction is a very common process which would be seen in the downstream operations of many chemical and biochemical industries. Leaching is a process in which a light solvent feed is fed and another heavy solvent feed is fed. The heavy solvent feed basically contains a component of interest which gets transferred to the light solvent feed, and the light solvent feed leaves the system as an extract, whereas the heavy solvent feed leaves the system as a raffinate. So basically there are two immiscible solvents with different specific gravities. It is ensured that at least one component of interest is transferred from the heavy solvent feed to the light solvent feed, and this system can either be a liquid-liquid extraction or a liquid-solid extraction. You need to be familiar with the terminologies which are used here. A light solvent feed is the one which has lesser concentration of the component of interest, and heavy solvent feed would have the higher concentration of the component of interest. Extract is the product stream which contains the component of interest, and raffinate is the waste stream which leaves the system. The raffinate could either be discarded or be recycled. You also have an absorption or a desorption system which looks very similar to the extraction process which we looked at. So in this case the difference is there is a liquid and a gas instead of two liquids or a liquid and a solid. You have the liquid which flows from the top to the bottom because of gravity, and gas is pumped from the bottom and leaves through the top. Gas itself is not transferred, liquid is also not transferred usually. However, there is one component which is transferred between the liquid and the gas. In case of absorption, the liquid absorbs the component from the feed gas, and in desorption the component leaves the liquid and enters the gas. So these are the two systems which are similar and we have been seen in many chemical and biochemical industries. Let us look at a simple example problem which will help us better understand these systems and perform material balance calculations for such a system. The problem statement says 200 liters per minute of aqueous solution containing 10 grams per liter of streptomycin is contacted by 10 liters per minute of organic solvent. The exit aqueous solution contains 0.2 grams per liter of streptomycin. Determine the mass fraction of streptomycin in the exit organic solvent, assuming that streptomycin is the only component that transfers. Assume density of aqueous solution is 1 gram per centimeter cube and the density of organic solvent is 0.6 grams per centimeter cube. Now let us try to convert this word problem into a flow chart. Before we do that, we first need to identify the basis for solving these problems. For this particular problem, we have multiple flow rates which have been given. As I had mentioned earlier, the way you define a basis is based on what information has been provided to you. Here, because multiple flow rates have been given, you could either choose all the flow rates as the basis, or you can choose the time as the basis and convert these flow rates into volumes and masses respectively. So for this example, I will be using the flow rates which have been given as the basis. So we can write the basis as given flow rates. Now that we have identified the basis, the next step is to convert this word problem into a flow chart. So this process is an extraction process which has two inputs and two outputs. The first input is an aqueous solution which enters into the system containing the streptomycin, and the second input is an organic solvent which also enters into the system but does not contain any streptomycin. So you also have two exit streams, one being the extract which is the organic solvent leaving with the streptomycin, and you also have a raffinate which leaves the system as a waste product, which is basically the aqueous solution containing very low concentration of streptomycin. Now let us label this flow chart with all the information that has been given in the problem. So this is an extraction process and you have an aqueous solution entering the system at 200 liters per minute and it contains 10 grams of streptomycin per liter and the density has been given as 1 gram per centimeter cube. You also have the organic solvent which is entering the system, which is entering as 10 liters per minute containing no streptomycin. So, the density of this organic solvent is given as 0.6 grams per centimeter cube. We have two exit streams. One is the aqueous solution which contains 0.2 grams per liter of streptomycin and you have an organic solvent which is the extract leaving the system as the product. We do not know the concentration of streptomycin in this particular stream. Having written all this information, let us try and solve this problem. Extraction is a process where two immiscible liquids come in contact with each other. These have two different specific gravities, which means there is actually no transfer of liquid which is happening. Only the dissolved component streptomycin is being transferred from the aqueous solution to the organic solvent. This means the volumetric flow rate of aqueous solution which is entering will be equal to the volumetric flow rate of the aqueous solution leaving. Similarly, the volumetric flow rate of the organic solvent entering will be the same as the volumetric flow rate of the extract which is leaving the system. So, this means these systems would have a flow rate of 200 liters per minute and this would have a flow rate of 10 liters per minute. As I had mentioned in the earlier classes where we discussed the fundamentals of material balance, it is ideal not to use volumetric flow rates while we are writing material balances. So, we can convert these into masses using the density that has been provided. So, now that we have the volumetric flow rates for these two streams, we can actually convert these volumetric flow rates into masses, and if we were to write a total balance equation, we would find that the equation is trivial because all the total masses of each of the streams are known. So, it does not make sense to write total balances for this system. Instead, we can start with component balances. Let us try to write a component balance for streptomycin. Streptomycin balance would be input minus output plus generation minus consumption equals accumulation. So, this being a system without any reaction, we would not have generation or consumption, and considering the system to be at steady state, we would also have accumulation to be 0. So, we end up with an equation which is input equals output. What are the streams through which streptomycin enters the system? The streptomycin enters only through the aqueous solution. The organic solvent does not contain any streptomycin. So, this means the input stream for streptomycin is 200 liters per minute times 10 grams of streptomycin per liter. So, the mass flow rate of streptomycin into the system would be 2000 grams per minute. Now, we need to calculate the output flow rates for streptomycin. We know that the concentration of streptomycin in the raffinate solution which is leaving is 0.2 grams per liter. So, in the aqueous solution you have an output of streptomycin as 200 liters per minute times 0.2 grams per liter. So, this means in the aqueous solution you have 40 grams of streptomycin leaving the system per minute. Now, if we were to continue with the balance equation, we would have 2000 grams per minute of streptomycin entering the system is equal to 40 grams per minute of streptomycin leaving through the aqueous solution plus this mass of streptomycin leaving through your organic solvent. So, this would be 1960 grams per minute. Based on the balance equation, we have now identified that 1960 grams of streptomycin leaves the system per minute in the form of the organic extract. We now need to calculate the concentration of streptomycin in the organic solvent, which is the extract. We know the volumetric flow rate is 10 liters per minute for the organic solvent. Considering that the concentration X of streptomycin in the organic solvent, which is the extract, would be 1960 divided by 10 grams per minute divided by liters per minute, giving you 196 grams per liter. So, this gives you the concentration of streptomycin. This gives you the concentration of streptomycin in the extract. The question asks for the mass fraction of streptomycin in the extract. How do we convert this concentration to mass fraction? For converting concentration to mass fraction, we first need to have an understanding of what the mass fraction means. What is the definition for mass fraction? Mass fraction is defined as grams of streptomycin per gram of solution. So, for calculating this, we would first be required to calculate grams of streptomycin per gram of solvent, which is easy to get from your concentration. Let us first do that. Grams of streptomycin per gram of solvent would be equal to the concentration of streptomycin, which is 196 grams per liter, which needs to be converted to grams per gram. So, that means 1 liter of solvent needs to be converted to mass or grams. How would we go about doing that? We know the density of solvent, so we can convert this liters into grams of the solvent. So, that would be converting first liters to centimeter cube. We would have 1 liter of solvent divided by 1000 centimeter cube times 1 centimeter cube by 0.6 grams of solvent. So, now this liters, which is here in the concentration, and the liter in this conversion factor can get cancelled, because both of these represent 1 liter of the solvent. The centimeter cube of these two terms can also be cancelled, because both of them represent the volume in terms of centimeter cube of the solvent. However, the grams terms cannot be cancelled, because this represents the two different grams. The first one, 196 grams, represents 196 grams of streptomycin, and the denominator represents 0.6 grams of solvent. So, this is why you would end up with a dimensionless number in terms of this particular mass ratio, but this would not be unitless. So, you end up with the value of 0.3267 grams per gram. So, this is the mass ratio. As I already said, mass fraction would be grams of streptomycin per gram of solution, not per gram of solvent. So, now we know that there is 0.3267 grams of streptomycin per gram of solvent, which means 0.3267 grams of streptomycin is present in 1 plus 0.3267 grams of solution. Basically, the calculation goes like this: mass fraction is equal to mass of streptomycin divided by mass of solution, which is mass of streptomycin divided by mass of streptomycin plus mass of solvent. So, the ratio is 0.3267 divided by 0.3267 plus 1, giving you a final value of 0.246. So, this is the mass fraction of streptomycin in the extract. I hope you were able to follow this problem. Please try this problem by yourself so that you would be able to understand the fundamentals which are explained here. This would be a simple example problem which uses the concepts of mass fraction and mass ratio and also explains how material balances can be written for this type of a system. Let us move on to the next type of a process. Dehumidifier is a common process which is seen in many chemical and biochemical industries. Here a feed gas, which is considered to be a moist gas, enters into a dehumidifier and you have two exit streams, one being the exit gas and the other is the condensed liquid. So, the feed stream contains a condensable and non-condensable components. So, condensate which is formed is the liquid which contains only the condensable components, and you have a dry exit gas which contains the non-condensable component. So, the exit gas does not have to be fully dry, it can still contain some of the condensable component along with the non-condensable components. You also have the reverse of a dehumidifier which is called the humidifier. The feed gas is the drier gas, it enters along with a volatile feed liquid and the exit gas ends up being a wetter gas compared to the feed gas. So, these two systems are very commonly seen in many chemical and biochemical processes. We would need humidified or dehumidified air because we would want to maintain the concentration of water vapor present in the air to ensure that the processes take place as required. For this reason, dehumidifiers and humidifiers are used very commonly depending on the environment in which the processes are taking place. In case of a humidified air, you might end up with a gas which is either saturated or not saturated. In some cases you might want saturated air which is saturated with the volatile component. Here is an example problem for humidification. An experiment on the growth of certain organisms requires an environment of humid air enriched in oxygen. 3 input streams are fed into an evaporation chamber to produce an output stream with the desired composition. Liquid water which is fed at a rate of 20 centimeter cube per minute, the second stream being air which contains 21% oxygen and the rest is nitrogen, and you have the third stream which is pure oxygen with a molar flow rate of 1/5 of the molar flow rate of the stream B. The output gas is analyzed and is found to contain 1.5 mole% water. You are asked to first draw and label the flow chart for the process and calculate all the unknown stream variables. So, let us now first start with identifying the basis for this problem. So, the basis for this problem would be all the flow rates that have been given. So, specifically we have the flow rate for stream A which is liquid water and it is given as 20 centimeter cube per minute. So, we will assume the basis as given flow rates. Now, let us try and draw a flow chart for this system. So, this is a humidifier which has 3 input streams and 1 output stream. So, you have the liquid water entering at 20 centimeter cube per minute and you have oxygen which is entering into the system as pure oxygen, and you have air which is entering the system containing 0.21 moles of oxygen per mole and nitrogen is 0.79 moles per mole. So, we can assume that the molar flow rate for the stream is n dot 1 and it has been given that the flow rate for pure oxygen is 1/5 the molar flow rate of stream B, which would mean this oxygen stream has a flow rate of 0.2 N1 dot. You have an output stream, let us just assume the flow rate to be N3 dot, and this contains 1.5 mole percent of water, which is 0.015 moles of water per mole. So, the rest would contain oxygen and nitrogen. Let us assume that Y is the mole fraction of oxygen in the exit stream, which would mean you can write the mole fraction of oxygen as Y moles of oxygen per mole, and knowing that all these mole fractions need to add up to 1, the mole fraction of nitrogen can be written as 1 minus 0.015 minus Y moles of nitrogen per mole, which comes down to 0.985 minus Y moles of nitrogen per mole. So, the volumetric flow rate which has been given for water should also be converted to molar flow rate, so that we would have all the flow rates in terms of molar flow rates and we will be able to apply them easily. So, it is important that we convert the flow rate of water to molar flow rate instead of mass flow rate. So, we will call the molar flow rate of water as N2 moles per minute. Now that we have drawn the flow chart, let us go about and try to solve this problem. As usual, we can write total balances and component balances for any of the system given. Let us first start with the total balance. So, the total balance for the system would be input equals output. So, the input is you have N1 dot plus 0.2 N1 dot plus N2 dot equals N3 dot. So, all these are the molar flow rates which have been given. Now, we can calculate N2 dot because we know the volumetric flow rate of water. So, N2 dot is calculated as 20 centimeter cube per minute multiplied by its density, which is 1 gram per centimeter cube, which again is converted to number of moles by dividing it with molecular weight, which is 18 grams per mole. So, now this centimeter cube gets cancelled, grams get cancelled, and you end up with 20 divided by 18 moles per minute, which is 1.11 moles per minute. Now that we have N2, we can substitute it to the first equation. We can also write a component balance for water. So, let us write this water balance. So, the water balance would be again input equals output. Input term for water is only through the liquid water stream. We know the molar flow rate is N2 dot is equal to 0.015 N3 dot. Now that we have already calculated N2 dot, we can calculate N3 dot from this equation. So, N3 dot is equal to 1.11 moles per minute divided by 0.015, which gives you a value of 74 moles per minute. So, the final humid air which is leaving the system is leaving at a molar flow rate of 74 moles per minute. We still need to calculate the concentration of oxygen and nitrogen in the final stream. Only then the entire flow chart would be completed. What balance can we write to do that? So, the total molar flow rate of the product stream has been calculated to be 74 moles per minute, indicating that 74 moles of humid air leaves the system per minute. We still need to calculate the molar flow rate of air and the oxygen which is entering the system. This we can do by substituting N2 and N3 in the first equation, which is the total balance equation. So, substituting them there, you would get 1.2 N1 dot equals N3 dot, which is 74, minus N2 dot, which is 1.11. Thereby, you can calculate N1 dot as 60.7 moles per minute. So, the molar flow rate of air which is entering the system is 60.7 moles per minute. So, the molar flow rate of pure oxygen which is entering the system would be 1/5 of this. So, thereby your oxygen flow rate would be 0.2 N1 dot, which is 60.7 divided by 5, giving you a value of 12.14 moles per minute. So, now we have calculated the flow rates of each of the streams. So, we can fill that information there. So, in this flow chart we have the flow rate of air, which is 60.7 moles per minute. We have the flow rate of water, which is calculated as 1.11 moles per minute, and we have the flow rate of humid air leaving the system as 74 moles per minute, and the flow rate of oxygen entering into the system would be 12.14 moles per minute. Now that we have all the molar flow rates, the only thing which remains is the concentration of oxygen in the humid air which is leaving the system. To calculate the concentration of oxygen and nitrogen in this humid air, we would have to write another component balance equation. We can choose to write oxygen balance for this, and that is exactly what we are going to do. For writing an oxygen balance, you again have input equals output. Oxygen is entering the system through two of the streams, one being the air stream and the other is your oxygen stream. So, you can write this as 0.2 N1 dot plus 0.21 N1 dot, and the exit stream would be oxygen leaving through the humid air. As concentration of oxygen is Y, we will say it is Y N3 dot. We already know the value for N1 dot and N3 dot. Substituting those values there, we can write it as 0.2 times 60.7 plus 0.21 times 60.7 is equal to Y times 74. So, solving this equation, we can calculate Y as 0.336 moles of oxygen per mole. So, now with this we have the composition of the exit stream also. The exit stream would now contain 0.015 moles per mole of water. It would contain 0.336 moles per mole of oxygen, and the rest is nitrogen. So, nitrogen would be 1 minus 0.015 minus 0.336, giving you a value of 0.649 moles per mole, and the total molar flow rate of this exit stream is 74 moles per minute. With this, we have solved for all the parameters which are there in this process, and we have completed the flow chart. Hopefully, the concepts which we covered through these examples and through these processes have helped you understand the fundamentals for performing material balance calculations in non-reactive systems. There are more examples and more processes which we will look at. So, we will do that in the next class.